decade resistance boxes.
Got
And,
Okay.
and then they have that heat kit box that
What box? Heat?
it was called the heat kit,
Heat kit.
resistance box.
Okay.
And it was this was one that went in weird increments. But it was the one that we used for the unknown resistor.
I see. So, did you bring this up to someone? Maybe.
I just ran the lab this morning.
Yeah. So,
I mean, I understand the concept, and I think that we could probably do a better job. I think we could use, we could still build the same apparatus.
Because that's not, it doesn't sound good at all, but I think we should bring it up to someone like Tori's the right person, and then he should.
I might bring it up to him and just tell him that I had a very, my class had a very hard time with getting it all to work because I kept on having to.
It's just not okay.
Replace. And I'd replace it with something that was already broken. That would be frustrating. So we ended up, not everyone was able to complete the lab because we started getting time.
I see. Yeah.
So, and it is, I think I might be the first group that does it. So all the bugs kind of come out then.
Let's see. Yeah, I don't know. I think Bob is the right person to inform. I think Scott, right? Scott permanently runs them. And, he's aware of these things. But yeah, we should bring it up. Yeah. I'll try to mention it to Chair if I ever get a chance. Yeah, good. Okay. Hello, Alia.
Hello.
Oh, that's really low voice. Let's see. Maybe it's my end. It's my volume. Can you speak again, Alia?
Yes. Hello, Professor.
Oh.
Do you hear me?
Yeah, it's very low voice. I'm wondering if it is my end. That is, if I can. We can hear you, but it's a little lower. Let's wait for others and see if it is your end or my end.
Okay, let's see.
Yeah. Where are others?
I don't know.
There's something. Ah, yeah. Moses. Haven't graded your homework yet? Okay.
I did have kind of a question on the homework that we just submitted.
You have a question? Or?
On the homework that we just submitted, yeah.
Okay.
Can I ask you?
Yes, I think so. Yeah. You think it benefits everyone? Sure.
Yeah. I mean, it was kind of on the very last part, part E. I didn't quite see how the La Vida symbol came in with the -1 cross E.
Yeah, I kind of forced that one. I was pointed like it's half of the last part of the.
Maybe that is okay. All of you say that. Maybe there is an issue. Okay, let's see. So before others come, maybe we can work on that.
But I was just passing it off as that I'm more familiar with the using the levees set symbol and the chronic delta and kind of new with those. But then you and I talked yesterday about the
indices.
the difference of the indices. And I think that's the thing, is being confident about messing with the indices.
Okay. First of all, maybe I should say that in all this, except I think after a month or so, as of now, we represent this to the A1, A2, A6, the three components of the vectors. As far as we are in 3 dimensions, it doesn't matter. This is the thing. This is actually equal. When we go into 4 dimensions, like very soon, probably starting today, actually, we're going to do relativity, then this is now the time component. Like this is still true, but there will be a 0 component. This is the time.
Mhm.
For any vector, this will be minus. Right, so that will change fine. But we haven't done that yet. So for our purposes, this is exactly the same. And what you is talking about, I think, is this, right? Del I. So there's a vector. There's 2 vectors. This and this is kind of dummy, like that's the vector sign, but then specifying that that's the I component. So we don't really need that. But here, minus J I. And Rob pointed out that the typo in that, so which I corrected today morning, it's too late, this was, but hopefully you guys realize that otherwise it is 0. So, okay, so yeah, so we have Luke. Can you hear? Can you say something?
Yep,
I want to check.
hello.
Yeah, so I think Luke's audio is correct. Alia, your voice is a little low, but I think we can survive. Just make sure whenever you speak, let's speak a little louder, maybe, Alia.
Okay.
Yeah. Okay. Okay, so that's and there was a charge Q in front of it, if I remember right. Or is it just there's a Q? Yeah. Right, that's, and let's say whatever this is, what should I call this? C I J. That's good enough. So that's a vector, or that's a tensor. No, wait, that's not a vector. That's constructed out of 2 vectors. And now the problem was, what was the
The
issue?
Q is distributed even to both of them.
Of course, dimensional.
The problem is show that that's equal to epsilon ijk, the kth element of B, which is also equal to -1 cross B.
Yes, yes.
So without the Q.
Without the. Q.
Yeah.
Okay. Notice that B. Yeah. First of all, just look. I mean, remember cross product, right?
Yeah. I mean that part's.
That part is clear, right?
Mhm.
So we have B vector is equal to del cross A, correct? And this part is clear. You're saying Bi is equal to epsilon ijk del j ak. Correct. So we want this to be on the other side, right? Or we want this to be on the left. I think that's the challenge you're having. So multiply this out, right? So let's multiply I. So the epsilon I m n bi. I cannot use jk because I have used it up here. Whatever I do on the left, I have to do on the right. So I m n I g k. That should be correct. Agreed. This is we can use an identity. Like this is index if you're familiar with that. Otherwise, this might be a mystery, but this there is an identity that this is mj nk minus mk nj. And that's equal to still in the code space, yes. So j, so this can be collapsed. So this is del m a n minus del n a m which now if I, at this stage, I can actually write it back in terms of IJKs. So this is, I'm replacing all the M with the I, N with the J. That's equal to epsilon I, J, K, and B, I. Is that the challenge? Or-
Well, I can also, I wasn't clear how then the right-hand side then equals -1 cross B.
1 cross B. Yeah.
-1 cross B.
-1 cross B. Okay, so we want to write this as a cross product, right?
Yeah.
So, so I would like J to have some vector associated with it, because when we want to see it as a cross product, so let's say this is K I J D I, right? That's good enough,
Yeah.
right? And now, typically, epsilon comes with 2 vectors, right? But there's only one here. So let me manipulate this way. So I'm going to introduce a new, so J I'm going to move. So let's say this is M, and B I keep it as it is. And now this is del M J. Right? That's perfectly fine, because when I collapse this, I'll get the J. That familiar, like the freeness with which maybe if your index notation, if you're not free, that piece could be a little unfamiliar, but hopefully we'll do this some of it in the next few classes, maybe somewhere we'll see. Okay. Once you have here, so this is the cross product, right? If I want to write it as a vector, so this is B crossed with this. I want to see it as a vector, but only the first part is a vector, right? This is a double, this is a tensor if you want. So M part is getting crossed. So this is 1, but so if you want, this is an I. So this is the ith component here, and that's the mth component here that's getting crossed. Right? So, but the free version is this. And then this is a tensor now, because think of this as having 2 pieces, 2 vector signs. First one is getting a vector, and the second one stays as it is. But, and the free component will be I is sum to M is 1, so it's KG. And what happened to, how did this become a K? Hold on. Something is wrong here, right? Oh, so this was K, right? Something went wrong. MN, yeah, so that then I was doing, I did I, and, yeah, this should have been a problem here, right? Because IJ is free here, IJ is not free here. So I think I messed up. Sorry, let me do this again. Okay, this one was M gets replaced with I, N gets replaced with J. So, but already I have used up that I there, so I had to replace K, that with K first of all, and M with I, and N with J, right? That's okay. Sorry about that. Then again, do the same trick. So now this is, I want to write this as I and J to be the free components. So this is epsilon I, J, K, K. So that's epsilon I. Now J, I want to write this, let me write, this is minus, right? So, because B, I want to keep it inside. So I, K, J, B, K. And this is a minus sign because I changed from K to this. So this is I minus K, B, K. So I say this is M times B, K times del M, G. Is this helpful? And this is nothing but minus of B crossed with 1, with the index being I and J. K is summed to B, M is summed. this, and this is now a tensor if you want, so we'll see. What's the challenge, Rob?
I see what you did. That was just one of the only things that I managed was the epsilon kijbk. And,
Yeah. Oh, yeah, yeah.
but that was.
Yeah, this is a little, I can, especially going from here to here, that's non-trivial. But once you see it, I'm just multiplying a 1 there. I'm just multiplying a 1 there. And why? Because I want to get that structure in there. Because this is just a vector, right? To write a tensor in terms of a vector is hard. Right? So I want to introduce a tensor in there and then collapse it with a B. So this is the best I can do. Because you cannot write a tensor in terms of a vector alone, I suppose.
No, the only thing is that the result was supposed to be minus 1 tensor, identity tensor cross B.
So it's wrong?
It's reversed. The cross product is reversed.
Okay, let's see. So this is, did you have this relation in between in the notes? Is this correct? Does this match?
That looks, I did not go that route, but that looks.
Well, the top of that line, it's in the notes, it's IJK, BK.
Yeah, that's okay, because K going twice is okay.
Yeah, yeah, okay.
That's fine.
Yeah.
Okay, so this is correct, right? So let's see what's the mistake I made. Okay, I flipped I and a K, so that's a minus, right? So that's correct. And now this is K, and I wrote MJ, that's perfectly fine. And now this is the cross product of K and M. K, this is the cross product of K and M, so it's K and M.
Couldn't you insert the identity to the left of BK?
Oh. I can actually move this wherever I want to. That's one thing. Like your point is that should this be like this? Del MJ DK? Is that?
Oh yeah, yeah, but that doesn't fix.
Yeah, it should not matter because these are numbers, right? Here it matters. Now I have to read this out. And from what I can see, this is K and M. This is the first vector, that's the second vector. So I want to keep that in that order, right? B cross M. Like the cross product is the first times the second. So it is necessary that B comes before I. If I want to write the other way, then I have to flip the sign. It seems to me that this is what it is. So let's see the problem. Okay. Give me a second. Yeah, that's okay. I think that's fine. I think that's also correct. So let's see that. I think that is also correct. You have something?
I was just going to say that perhaps, I mean, is it necessary that we keep I as the free index, or could we write delta MI and have J be the free index?
Here you mean?
Yeah.
Here we don't have it. Left hand side is the free index, right? Whatever you choose here has to be there. Right?
Right.
But then you're probably saying Why not use the I?
Well, yeah, once you have the right-hand side, then it's like, yeah, we have two indices that could possibly be free.
Yeah, so probably that's what I'm going to try, probably. I'm not sure exactly what you have in mind, but maybe that's what it is. So yeah, so I think this is correct. So now let's do the other way, right? We want to keep this in the, why not keep this in the front, right? So this is, how do I do this? So we wanted to do this, correct? I think that's what it says, I, J, K, E, K, right? That's also perfectly fine. But now I want to write some vector in front. So this will be I, M, K, delta, M, J times E, K. And now I want to cross the M and a K, so I can flip this, right? Actually, J or MJ doesn't matter. Let's say J. Oh, but I'm again getting the other way, right? No, I want that one crossed with K. So first I don't write this. I want to keep B in the middle. Sorry, B in the middle, right? Or is it B in the middle? Oh. This is one crossed with B, right? So this is the last one has to be B. So this is, I think I wrote it correct. I, J, K, B, K. And I want to put in a 1 in between. So epsilon, I, M, K, and delta of J, J, M, and BK. But now this is the cross product between M and K, which is J. Oh, I have to go to the other side. Yeah. Yeah, so this is 1, right? So this is 1 crossed with B. And that's it, I suppose. That's no minus. That's the minus something. I think so. Why am I getting confused? Okay, let's go forward. Maybe there is a typo. Can we check that? So does it work otherwise?
What I ended up submitting, I said that if we swap I and J on the left-hand side, then you could have a, like, because I wasn't sure, because there was a typo, right? It's
Oh,
at
because
least
of
in
that, you
line
guys
12.
lost confidence there, because this could have been a minus sign there also.
Yeah, I mean,
right?
I assumed that line 13 was the same as line 12 on the, yeah. But I couldn't figure out where the negative came from. So I thought on the chance that the indices are swapped, that would, I don't know.
Yeah, I'm also confused at this stage. I think these two are related this way, but this is off, right, by a sign there. So let me check and tell you guys. Okay, instead of me fixing, I mean, actually I can fix it by checking 12 actually. So if 12 is correct, then, and then also, I mean, this 14 also, right? Then I'll start doubting 14, right? Because this is me writing it. So this is not a standard thing. So, but this is existing. This is relatively standard in the sense it exists. So I just try to make sure that everything is consistent. So it's better I go back and check on it. Just consistency is the problem.
Can we
More
try
like-
one more thing?
Yeah, sure.
So if instead of replacing the J index with M, if we replace the I index,
Yeah,
would that change the sign? I think that's what Moses was suggesting.
We can do that also. We can try that also. Right, so here the suggestion is to replace the I index. So you want I M epsilon M J K B K, right? Yeah, this does come out, but then I should have checked the factor. Yeah, this does seem to come out correctly, right? Because this seems to suggest that epsilon minus J M K, is it visible to you guys? Yeah. Okay.
Yes.
Minus J M K, then delta I M B K. So that's the cross product between M and K. So that's indeed minus 1 cross B. Oh, that's okay. What went wrong here? Come on. I cannot get through the control. Okay, let's think. I can do this also. J M, that's M J. J M. And M and K getting crossed. Is okay. I'm doing something really silly.
Well, I don't feel as bad.
Hmm?
I said, no, I don't feel as bad.
Might be bad now. It's not bad. I think this has to be consistent. And this is no way. Oh, let's begin again. It's visible. Little steps. Okay, so that's epsilon I J K E K. You guys just told me two ways of doing this. One is you say M J K, and this is I M E K. And you want to write this as a cross product. Cross product is the first times the second times this epsilon J M K, where this is this I would say is minus J. Oh, this is not okay, right? Yeah. This is, I think, yeah, this is okay. I understand probably now. Yeah. Okay, so this is the one crossed with B. And notice, yeah. I think I understand. Okay, so this is the I G. Got it. Yeah. Okay, let's do this now. Okay, I think this is correct. Okay. Now let me come here. I think I know what's the trouble. Let's do this again. Yeah, so this is I and M K delta J M and E K. Yeah, this is okay. Now notice what is happening here. I should, in principle, write J this side. Like, okay, nothing wrong here as such. This is I. If you allow me to read it this way, so the cross product is this component versus this component. Now the point here is, if I were to see this as 1 cross B, that's perfectly fine. But what are the indices here? The left index is J and the right index is I. Which is not we want. We want to write it as a tensor with index ij. So this is not what we desire. This is perfectly fine, but this is not what we desire. Like on the left hand side, we want I to be on the left and j to be on the right. So this is okay, but this is not useful. Like this is okay as far as you read this as ji. So here I was not being careful that whether I is on the left or j is on the right. Is that clarifying the point?
So could we then just do one more step where we swap the indices and add a negative sign? Or
How do you swap the indices? You have to be careful. You have to go back this way, right? Because it is not very obvious. That's the whole point. That it's not very obvious how this cross product works with one. Like with little practice, you will surely say, "Oh yeah, that's okay with the swapping. It's perfectly fine." But I would say since at this level of doing it, we need the only way to prove that is to go back this way and come back here. Yeah, but yeah, if you write it, yeah, you should be correct in swapping that. Did I clarify that? Like the index here is ij and the index here is ji, so which is crucial. That needs to be respected. Then okay, okay. Yeah, good point. I mean, that's a little subtle there, but yeah, I think it has to deal with the fact that one is not easily put into the cross product, right? Yeah. Okay, hopefully, is that little? At least that's a correct version. I don't since I struggled, I cannot expect you guys to have followed it completely, but hopefully, at least that clarifies, at least from my perspective. Any concerns, questions? Luke, you are not satisfied.
I guess I'm a little surprised that it looks like the cross product J and I are switched. Like, oh no, wait.
Because J and I are not cross, right? Cross is between M and K. Right? And
Right, but so in the left sort of,
here it is.
yeah, I just wasn't sure how you went from like epsilon J MK delta IM to that being I on the left and J on the right.
Oh, so let's do that again. So, oh, actually here it is okay, right? If you want, I can write this in this form. Minus of delta IM epsilon J MK and DK. And this is a cross product between these two quantities, right? Because this decides the order of the cross product. And first vector is free. That's a free index. That's gives me with the J. And MK is summed, so that decides the order of the cross product. So this is minus, so this is 1, which has an I on the left, and the second vector is J. So is that helpful? Writing in that way?
Maybe. So I see, I know that, yeah, I see how the order of the cross product is decided, but I don't see, it's not obvious to me how the order of I and J is decided.
Okay. How is the order of I and J decided? Okay, that's now a vector, correct? Okay, so yeah, let's go back here. This is surely I have minus, so this is a free index, I, correct? And that comes with the 1. So this is, if you want, this is a free index. This is the I. There's another piece in here, right? That is if you want M, right? And then there is this epsilon ijk, which takes care of this. So this has a M, this has a J M K, right? And this is B M. That way of saying.
Okay, yeah. So I guess in the first step, we should have not changed the order of INJ.
Here, like when I
No,
write it
at the very top.
at the very top. Okay, at this stage it is okay to do it, but yeah, if I were clever or if I was careful, I would have put this in the front just to avoid confusion. But this is not wrong. See, these are numbers. At this stage, I can write anything anywhere I want. It's only
Okay.
when I go from this to the vector notation, there is an inbuilt understanding that cross product is first vector on the left, second vector on the right. There is a rule there. Here I can do whatever I want. I can move things around. Like this is okay. But yeah, it is better to put this like this. It is good to read this like this. But surely not wrong. Does that help? Like, I think, again, go back to this, when you have C is equal to A cross B, right? This has an order, like that's important that we write it in which order it is. But if it is this, it doesn't matter how I write this, I, J, K.
Can you move the camera?
Oh. Sorry, so it doesn't help if I'm talking something.
Thank you.
Okay, so what I was doing is, this is C is equal to A cross B. I can write it in this way, or this is also perfectly fine. I, J, K, B, K, A, J. See what I think? In this notation, it's okay to write A and B wherever I want to, because this takes care of the order. The index takes care of the order. But in here, the order is important, and that's why I mean to say that it doesn't matter whether it is this or that. Does that at all help? Little bit? No.
I'm not sure. I think I need to think about it more because it seems,
Fishy.
yeah, I still don't see how the order of M and K decides the order of I and J.
I think what I like last time I tried. So there is this. Okay, I'm breaking this one into two pieces. Right? There are two vector features in that. It matters whether it is the cross product with this or this. If I'm crossing on the right hand side, I'm stuck with the M, and I have to do this. I can write that M, that's a B. And this together, this piece together, this is a vector, that's a vector, that's my J, if you want. Very diagrammatically speaking. I'm splitting this vector and then using one of that to cross with it, because I had to cross with something. Is that an inbuilt rotation, I think? Yeah, that's what it is, but maybe not very helpful. How about this? Think about it, come back. I think this is something where you have to think, I guess, make sure that it is, yeah. I think it is, yeah, I can surely say that this part is correct. And there is nothing, no mistake there, so that there's no confidence issue. Yeah. Yeah, surprising that. one typo can lead to so much. But this is good that you brought it up. Some non-triviality is surely there in this stuff, so it's not trivial. Okay, yeah, thanks to all of you for bringing it up. Right. Okay, you're missing. Sure. 1, 2, 3, 4, 5. Yeah. Okay. Shall I proceed? Or yeah, ask me again. Don't hesitate to ask me again if there is anything I'm missing in this or something. Michael? Is it okay?
Yeah.
Or yeah, I'm not saying that you're comfortable, but at least yeah, let me proceed and we'll see. Okay.
Yeah. Sounds good.
Oh, I didn't ask Aliyah. Aliyah, because I don't see the picture.
Yes.
Yeah. Any comments or questions? Your volume is very low.
No, thank you.
Yeah. Okay. Okay. So there's homework 6 I haven't yet posted, but I was deciding in what order to go. Somewhere I want to introduce relativity a little bit so that you get familiar with it, even though in principle you can get away without introducing it, but I think it is good to introduce it and get the notations and all clear. So I'll spend about a week or two on relativity because I started doing this, I think, since last year, I think. But I think it's beneficial. So we'll do, so that I was deciding on that side, that's why the homework is not there yet. So we'll do relativity. This will be due March 17th. So hopefully, if you have done classical mechanics with me by any chance, there will be a lot of similarity in the homework. It's reviewing the material in there. But I try to do it slightly differently in this.
This is the 17th of Wednesday.
Yes, because I'm supposed to get a shot. 16th then, right? Because today is 9, so it will be 16. Thank you. Okay, this is correct, I guess, plus 14. Did you guys work on your shots, and did anyone make progress with that? With the
Vaccines?
what is it? Yeah, vaccines. Yeah, I mean,
I'm getting mine on the 17th as well.
okay. Yeah.
Thank you for sending those links.
Okay. It's minimal. Yeah. Okay, and Rob got his, I guess, Friday. Yeah.
You might need an ibuprofen or two the next day, but other than that.
Did you have anything in the first one?
Saturday, I was experiencing very, very light symptoms. And so I took an ibuprofen and covered up and slept it off for a couple hours and I was fine.
Yeah, that's what I've told. Yeah. And those who did not have it in their first one will probably have it in the second.
Mm.
They're efficient down there, I'll give them that.
Yeah, yeah. Okay. Okay, so this was about the vaccinations I was talking. Yeah, anyway. So. Okay, so let's go back and get the full Maxwell's equations in hand. And here I want to talk about how probably you guys are all familiar, if not, special relativity was completely motivated as a direct conclusion from the Maxwell's equation. So it's kind of a nice thing. So I want to motivate that, and just as a historical, just to give a historical perspective, it is 18, I think it is 18, not sure, like between 1860 and 65, probably 64, I think, is when Maxwell gave his equation. Right. Remember way back all the way to 1800, already Faraday had shown pretty well that Faraday's law, whatever we call it, change in magnetic field creates electric field. So everything was there except one of the terms in the fourth Maxwell's equation that we write down. So that was not available. And Maxwell very brilliantly, just using logical arguments like theoretical conclusions, he argued that there has to be that term. And that led to this equation. But the nice feature was that immediately this implied that there exists waves, like so electric and magnetic field. That's what we will do today. Electric and magnetic field obey wave equations, which I have, I'm sure, done a few number of times in the class. I've shown that they obey wave equations. And if they obey wave equations, that means you can send a wave, right? Like exactly like you have ocean waves, you can talk about electric and magnetic field waves. But imagine the situation where before that, that was not realized, right? So that's a very big conclusion you make. And immediately this was searched for, and inside a room, going from one corner of the room to the other corner, that was done by Hertz, experimentally verified by Hertz, but it took some time. How much time? I think 80s, 1880s. Let's put it 1885 to 1890. Confusing to me because that's when this what other experiment where what's the experiment where interference experiment where the speed of light was tried out.
Michelson-Morley?
Yeah, Michelson-Morley experiment is in 85, right? So probably it was before that. Yeah, around 85 to 95. But surely, I think there were effects that were seen right in late 70s. But conclusively, this was shown only in this region. I think that's it. And it was all expected right after Maxwell showed it. It was everyone expected. They thought that this was just a matter of proving it, but everyone started believing in it very clearly. So that's the two points I want to highlight today. And the moment you say that there is something moving with speed of light, so you're talking about a wave that will move with the speed of light, and then you ask, okay, what if you move with another velocity? Will it move faster than that? And there was this issue that it was not obeying the standard relativity principle or the Galilean relativity principle. That's it. So there was a conflict between Galilean relativity and this. So I want to highlight that a little bit here. So let's go back to Maxwell's equation and see, first of all, let's see how you see the wave equations showing up. And yeah, I will do the, yeah, why not? Yeah, so let's see. So this is del dotted with, should I put the epsilon? Where should I put the epsilon? Yeah, I typically like to put the epsilon right in between here. That's rho. Okay. And then we have del dotted with the divergence of the magnetic field is equal to 0. Cross product of the electric field is equal to minus time derivative rate of change of the magnetic field, and we have the magnetic field del cross H is equal to time derivative epsilon E plus J. That's your for Maxwell's equation. If there is a material, of course, this becomes D and there are changes, but let's say we are outside the material, and even if we are not really overlapping with the charge and the current, there is a simplicity in here. So yeah, in your homework, actually, you keep all this. Yeah, let me just do this. It doesn't matter even if it's a repetition of homework. And we can work with the potentials also in the same step. Okay. So what we do is first let's take the cross product with respect to the electric field here. So that's L crossed electric field. That's equal to cross product and time derivative commute. So it's derivative of L cross E. Right, that should be fine. That's coming from this. This call it. Suppose I label them as a third equation. Use the relation for the cross product. We have L of L with E minus of L square. This is here, but they commute, so this can be written in this form. That's equal to del cross B is minus time derivative of B is mu naught times H, so that's mu naught can come out, and del cross H is time derivative of epsilon naught E plus J. This is the same as, let me take this onto the left hand side, to the right hand side, and we have minus del square plus mu naught epsilon naught T square of the electric field. Now that's equal to the divergence of the electric field is nothing but rho times epsilon naught. Right? So this is 1 over epsilon naught times the gradient of the charge density. And I would say this is minus mu naught times time derivative of J. So that's your equation, but now let's consider a region where the right hand side is 0. Let's consider a specific region. So what is happening here is that there is some source here. Some source here. There is another. We will need a detector, and a source both has to have current and charges in principle. So this could be a source, and that's a observation, right, or detection. Observer and a source, and here rho is 0, J is 0. So if you say these are far enough regions, in that region, rho is 0, J is 0. In fact, it's 0 everywhere around. So the right-hand side is not contributing to a significant amount. So what we have is a wave equation. This is a wave equation which tells that the Laplacian of the electric field is exactly equal to mu naught epsilon naught. So, okay. What do we mean by this is a wave equation? Let's just roughly talk about that. Why this is a wave equation, and in what sense is this a wave equation? If you want any questions at this stage, and I should say point out that there is a similar equation satisfied by the magnetic field. You will get the explicit equation for the magnetic field in your homework, but this is P also satisfies mu naught. This is homework. In fact, it will turn out that potentials also satisfy the wave equations, electric field, magnetic, all of them satisfy wave equations, except there are sources, of course, associated with that. But if you're outside the source, the idea is that they travel as a wave, and the wave equation decides their evolution in space and time. And then we are asked what is that constant, which we have already thought about before. Okay. Notice the idea is that suppose it is one dimensions, you have d by dz square, and let us say you have a function f of z and t is equal to 1 over, we call this velocity square, d by dt square f of ct. If you have an equation of this kind, the idea is what kind of solution satisfies this. And notice that there is a if you have a combination of z plus or minus vt, so suppose you had f to be of this form. It doesn't matter what this function is, but if the dependence is of this form, plus or minus vt. So there is some parameter v showing up, and if I were to think of this, think of the dependence of this kind, let me see what is the first derivative, the f by dz. I don't know, because what this will do is that whatever is the function f with respect to the argument, which is decided by z itself, and then the argument itself, derivative, use the chain rule, but the chain rule does not have to do anything because z is itself. So suppose this was the quantity, so this is decided by f. I cannot really decide it by f, right? So I need to know the function f to be able to do that. But what about derivative of f with respect to t? That's reasonably easy, because I can write it in terms of z now. This is the same as derivative of f with respect to z, because that's z is also the argument, if you want, of the function f. And then I can do d by dt of z plus or minus vt. So it's a chain rule, if you want. Or if I were to call this an argument, then that is how you would put it. And that is nothing but plus or minus v times df over dz. Maybe it will be better if I call this a new quantity, that I use a chain rule. And so maybe let me say that, if that helps at all. Probably this is trivial for you guys. Yeah, okay. So this is what should I call it? G? No. Capital letter. A, B, C, D, E, F, S. So this is the same as df by ds times ds over dz, which is just df over ds, right? So that's it. Does that help? And this is now maybe s ds by dt, and ds by dt is plus or minus v there. So this is, oops, plus or minus v times df by ds. Sorry for making this complicated. Okay, so second derivative with respect to z, second derivative of f with respect to z will be the same. Still on the board, yes. Will be the same as doing this with respect to z, and so this is d by ds times d by dz. What am I doing? So this is d by dz of df by ds. Bring that out. So that's d by ds of df of dz. But that I know is the same. Okay. And then do the same thing with this. Hopefully. Straightforward. So that's d by dt of df by ds, but plus or minus v has to come in. That's equal to plus or minus v times d by ds of df by dt, and that's the same as now v square times v square f over dt square. Why did it come in the wrong place? Did I mess up? Oh, because this is s square, right here. So, okay, so what that means is that d square f over ds square, this satisfies our equation. Doesn't that mean that? Because, yeah, so second derivative of the left hand side is equal to second derivative of f with respect to s square, and right hand side is equal to, there is already a velocity square, that's 1 over velocity square. All right, so that's a wave equation. So it doesn't, notice that we always think of wave equation, like what I was trying to highlight is that only sine and cosine are actually the wave functions, but any function of this form is actually a wave. A pulse, for example, which is really not at all like a wave at all, that also satisfies the same equation, and that's perfectly fine. Like exponential of minus z minus vt square, right? That's perfectly okay. Like this will look like this, and it's just that this point here will move like a tsunami. So, so that's perfectly okay. So that's a wave equation, and we have electric and magnetic field satisfying that. That immediately tells us that velocity epsilon and mu has the velocity interpretation. So we learn that epsilon naught mu naught is equal to, as I said, 1 over velocity in interpretation here, and we will call that the speed of light, and this is c squared. So this was first suggested by Maxwell, that the light that we see around actually is a wave, and immediately we talk about if it's a wave, what's the frequency, and so on. That was the first time that was suggested, and that's what Heinrich Hertz actually went and proved that. And before that, remember, when we have a wave, we talk about frequency and wavelength. So it was already there. It is not that wave was a new concept, but Hertz's contribution was so significant that the unit of this frequency itself was named after him, not during his time. I think it was later on, probably in the late 1950s and all, was established. And this, what is the value of C? Just for completeness, C, these days C itself is a constant, right? The SI units has been changed recently in the last decade or so. Now it is defined in terms of the speed of light. Speed of light is an integer now. Like it is not dependent on measurement. It is actually fixed to be an integer, and it is exactly equal to 299 if I can remember this correct. I guess not. I used to remember it. Whoa, I don't remember. Okay, help. Anyone else?
792458.
792458. Yes. Is that 458? Is that? 792 is correct. Yeah, because I remember it as the 8 subtracted from 800. So this is 458. Is it?
I think so.
Okay. Yeah, so that's it. Perfect integer. Nice too. Nice trivia. And mu naught is equal to 45 into 10 raised to minus 7. What will be the units of that? So that will be Tesla meter over amp. Mu naught I over R is magnetic field. So these two gets fixed, then epsilon naught can be is a derived concept in that sense. And epsilon naught then is equal to 1 over c squared. So C is about 3 into 10 raised to 8 meters per second. And it immediately leads to the idea that if this is the case, and since epsilon naught and mu naught has no material property dependency, right? This is a universal constant in every sense. And by universal constant, we mean that it doesn't change with position, it doesn't change with time. If you go to another galaxy, it's expected that the same equations will work. We don't have to change anything. And it doesn't have any apparent material property dependence, right? It's a property of the vacuum in every sense. And then that raises the question, the moment you say that there is some wave that can, something that can move with the speed, what happens if you go relative to that? Right? And it is going, if it is going to change, that means you're going to say that, oh, these properties change with time. Time or relativity decides those properties, and that's something striking. So that was the idea that immediately after Maxwell's equation, all these questions were raised. And remember, until 1905, until Einstein came, it was not resolved at all. It was a big. There was a lot of activity on it, a lot of, in the sense, fundamental work related to that. And it is interesting that most of the work that was going on was very interesting. Like there was this, what it was called broadly, very broadly called electron model. They tried, one of the things they claimed is that, or they thought was happening is that the inertia of matter, when we think of mass itself. So there is this whole electric field. The way one wants to interpret this is that there is a charge, and there is an electric field associated with it. Right? Think of it as rays of light, but they're physical. Right? Every small element of space has energy and momentum associated with it. And now there is this electron that is going to move. Whenever it's going to move, it is supposed to carry this whole weight with it. Right? So the whole electric field has to move with it. Like just imagine that. Think of you as having spikes on yourself and very long spikes. And now suppose you have to move around, all those spikes have to know that information, right? How much time does it take for the information from you, the tension, to reach the other corner? And there is a whole motion that was brought in. And Lawrence, and there was a whole activity. Everyone in those times expected that this is what caused inertia of a body that we know as mass. Inertia, by inertia I mean mass. How do you associate a mass to an object? The expectation was that this electric field, the inertia, because when you're trying to move, there is an inertia associated with it. That is what shows up as mass. So mass was no more thought of as just, like, for example, how do we define mass? As of now, we don't have a definition of mass. When we teach physics 205, we say, oh, mass is anything that occupies space. It's very rough. We don't really precisely define. So in this sense, when you try to define it, it becomes very elegant or very fundamental in that sense. So it was very interesting, but then Einstein came and spoiled everything. He gave a completely different interpretation. So everything stopped right there. I mean, because it was such a huge change, paradigm shift that the whole world stopped and everyone went on the other side. And these days, there is a lot of work associated with it. We just try to revive it in a new interpretation. Of course, their interpretation was different completely, right? So that cannot be correct. But is there any merit in thinking of an inertia associated with these fields on, which is still an interesting question to ask. But with that very vague points, let me proceed and say what how is relativity showing up in here. So I'll just introduce and bring it back later. So let's think of light. So there is a source. So there's a source of light, basically. And the idea is that light is now a wave in a sense. And there is an observer here, right? So there is an observer. And by this, I mean there is a wave that's going around, right? And this is moving with speed of light. Now this typically, the way in those days it was ray optics, that we know that this is actually a spherical wave, right? This is an observer can be here or anywhere around that. That's perfectly okay, but this is going to be a spherical wave. That's one point. And let's observe this using two observers. So that is, let's say this is the coordinate system. That is what the event that is happening is out there, an observer, source and an observer. And let's say there is an observer, which we'll call it the ground. Right? Now, then there is another observer, one here, which is moving, let's say, and that could be another observer two, which is moving. So this is position, let's say, position of one with respect to ground. That's the position of two with respect to ground. And of course, this is one more, right? This is all, I've shown it as one dimension, but it can be just tilted and as a vector equation, this is perfectly fine. So position of two with respect to one. So immediately I can read out what the connection between these quantities are. Whatever observer two measures or observer two measures with respect to ground will be related to whatever observer one measures with respect to ground plus, let me write the other way. So this is R21 plus R1G. That's a vector relation, generally valid. It doesn't have to be linear the way I have drawn it. So in general, that is true. Okay, so what I want to do with this is that now I'll start dropping this G here. Everything will be with respect to the ground, and there is an R21, right? And And the quantity that I want to talk about here is the vector source, that is R is equal to CT. So let's say a distance traveled will be equal to C times T. If this is going with speed of light, then this is going from one point to the other, and that will just take C times T as a distance. Since this is a distance, square it, that is better. So that's R square is equal to C square T square. This is in one frame now. So then notice there are two frames. Like I would like to talk about this and this. There are two persons observing the same thing. Their observation points are connected with this, and I want to make one of them move. I want to make one of them move with velocity. So that's what the goal is. But the observation, what are they observing is this, where R is the distance traveled between these two quantities, and that will lead to the idea that this is x squared plus y squared plus z squared minus c squared t squared is equal to 0. Notice that minus sign is a classic signature of relativity showing up. Oh, I'm okay.
Move the camera.
Damn. I keep forgetting it today. Yeah. Okay. Sorry. Okay. So I was saying that this observation, so this distance is r, and that how much distance it travels according to one of the observer is r is equal to ct, where r, and so there is a distance measure. So if you are to do this measurement or interpretation, first you have to talk about a distance and how much time it takes. So that's a two quantities that is going in. You can say these are change in distance, r minus r prime and t minus t prime. That's perfectly fine. Same observation is done in another frame. This frame which is moving, you say this is another, I don't know what he measures, and r prime, right? Whatever the difference is, that's equal to, and to be very general, we also say it takes t prime. That's a big difference that comes up with Galilean relativity, that Galileo would have said time is the same, time is absolute in that sense. But again, this was not obvious at all between 1865 and 1905. Based on a lot of struggles, it was realized that it's possible to have the times not to be the same, and we have our prime square is equal to c square t prime square, and then we say that okay, this new quantity is y prime square plus z prime square minus c square prime square is equal to 0. Right, that's two conclusions you can make. Again, one shouldn't accept that this is the way Einstein proceeded and do it. That's not what I'm claiming. I think Einstein pretty much realized this whole conundrum and somehow came up with it. I think it was just to make it all work. The logical conclusion probably was not exactly the way I'm giving this, especially when we do classical mechanics, we do it different. Actually the way Einstein likes to put it, I think, is that he will call this the principle of relativity, and that becomes the fundamental idea. That is like Maxwell's equation is, of course, the background in which he is doing it. Everything, in fact, the title of the paper is Electrodynamics of Moving Media, but he gives a lot of weight to principle of relativity, that these two, relativity is fundamental and everything else is secondary, which is how we understand it now. But here the context is different. Since I'm doing electrodynamics, I'm just using another method. Actually, that's what I should do it as a homework, right? There was a reason, I think this was this year, or at least a few months ago, in American Journal of Physics. Yeah, look it up, quiz, right? Or I'll try to put this in the homework. So there was an article, I think it started with there's 7 ways. Yeah, I think that's what he said. There's 7 independent logical ways of concluding or deriving Lorentz transformations. idea is relativity implies Lorentz transformations. And how do you derive that? He said there's, or at least he showed that there are 7 independent, very closely related to each other, but there are 7 independent ways of doing that. I'll try to give a link if you're not able to find it, because that's just a keyword I have given. It's in American Journal of Physics. American Journal of Physics. If you can find it on your own, that's good, but otherwise I'll try to put a link to that when I'm giving the homework. and yeah, so now we have this relation, and let me not do it now. I'll come back. I think it will be a good complete lecture. Then we'll start from here, and we'll propose that x prime. How is x prime related to x and t? Remember, Galileo would have said this is x minus vt, right? So Galileo would have said this, and t prime would have been just t. Right? That's it. Right? But let's be more open, and let's say this is some function of v. A is some function of v times x plus b being some function of v times c times t. Just for dimensional reason, I put in a c there, and then I had to put let's say, let me not use the letter c because c is already there, so let's call it e and f. Right? So e as a function of v times x plus f as a function of v times c times t. So suppose we keep this very general transformation and put this back and say that, oh, this should be satisfied. Like, that means to say that both observers should see the same physical effect. Whenever it comes to light, it is the same. Right? Different observers measure the same. If we put that condition, how far can we go in concluding anything about A, B, E, and F? And that will lead us to the Lorentz transformation. And then we'll very quickly summarize what we can do with Lorentz transformation, and then get back to radiation. Basically, we want to talk about light. Okay, let me stop here. Thank you again for allowing a few extra minutes. So very generic. Today's lecture was very common. Like many things you might be knowing, but I just wanted to fill in. Okay, thank you. And let me know again if you have problems with that epsilon ijk. So give it a thought, and yeah, you brought it up, Moses. Thank you, and I think Rob also mentioned it. Thank you. Okay, bye-bye.
See ya.
Yeah.
See you guys.
See ya.
Bye-bye, Michael. Bye, Alia.